For this presentation, I would like to introduce Mr. Luke York, who has done a project on an injection molding part design.
Once again, my name is Luke York, and I was chosen to do the injection molding part design for USI. The objective of my project was to create a stable part design that could be used in learning for both the students and professors alike. To do this, we needed the ability to use this within the courses offered here at USI. I needed to submit a recommended part design as well as mold type. An injection molding machine starts off with plastic within the hopper, and then the plastic is usually in a pellet form. After this, the pellets move down into the barrel where the screw will rotate, drawing the plastic forward in the barrel. There's a transition point inside the barrel where the plastic is under such high friction and pressure where this is what actually melts the plastic. You'll see heater bands around the barrel. What these will do is keep the plastic in a molten state. The plastic is then injected through the screw moving forward into the mold. During the injection process, the plastic will move through the sprue of the mold into the runners and at each cavity of the part. After this, the part is ejected, the part is cooled and then injected. So right here we have the injection cycle, going through the sprue runners into the cavities, cooling and the recovering of the sprue, and the part is ejected. And once again, the cycle restarts. The factors to mold design. The initial is the part design, the product that we are wanting to produce. After this is the resin types. This can be anything from an ABS material, which is used in plating applications, to a glass-filled polymer. And depending on the mold type as well as mold material, this can impact the part design. Quite often, a tool steel is used on more abrasive materials as well as larger batch runs. The cavitation runner system, cooling system, and injection system must be designed around one another to create the stable part design. The cavitation will decide how many products are produced in a single cycle of the machine. The runner system delivers plastic to these cavities. The cooling system will cool this mold into the solid state, and the ejection system will remove this from the movable side of the mold. This is just some key aspects of a part. We have the sprue, which is the inlet point on the part, and then the runner delivers this into the gates and the cavities of the mold. The gates are the inlets to these parts. When designing a part, you need to have two ideas in mind. This is the minimizing the stress on the material and the product that we are wanting to produce. When designing the product, you want it to have an equal thickness throughout the entire part. What this will do is this will allow the stress on the material to reduce. Along with that, if you notice in the center picture, this is a transition point. In the center picture on the top portion, you see a sharp edge. As plastic flows across this, the polymer chains will break. This will cause scale and splay, which is a defect within molding. Excuse me. The other three are decided upon on part properties as well as the engineering preferences. On the far right, we have drafts needing to be implemented within the mold. If we have a 90-degree angle, this can hang the part on the movable side of the mold, which can close up on this. This will damage the mold, which can cause flash. Flash is where a thin sheet of plastic breaks the parting line, which is where the two molds connect. The mold types. Here at USI, we have two different types. We have the mold base with the slide-in unit. This can be used in lean manufacturing and teaching applications within the classes offered here at USI, as well as SMED. SMED stands for single minute exchange of die. It does not actually mean a single minute, but rather a single digit, so under 10 minutes is the goal. The two-plate mold on the right shows us a single part design in one mold. Different aspects can be changed with different inserts, but not the entire part design itself. The cavitation is decided upon on three different factors. First is the cost. This is within the engineering of the actual mold, as well as the material within the runners. The runners are a common form of waste. The machine properties. This is done by the tonnage of the machine, which here at USI we have a 55-ton injection molding machine, and the amount of material that is able to be injected into the mold at any single time. tonnage is decided upon by the surface area of the part. So on the movable side, say that we have 10 square inches of a shadow cast onto the side. You multiply this by a factor of 5 to get the tonnage. So say we have 10 square inches times 5, roughly 50 tons. This is not the actual tonnage, it's just an estimate. And finally, production urgency. We don't have a production urgency here at USI, but in a manufacturing environment, this can be the difference between making a single part or twice as many in the same amount of time. The runner system, once again, this carries the plastic into the cavities of the mold. We need to multiply the runners 1.5 times the thickest portion of the part. What this will do is this will give us enough material flow through the runners to ensure that there's no short shots within the material. A short shot is when the cavities are not fully filled. If we oversize the runner, as can be seen in the left photo, just by a 1 cubic inch. Say we make this part 300 pieces in a shift, 3 shifts a day for 240 working days a year, we can waste around 125 cubic feet of material in a year's time. The runners must also be balanced within this mold. This means that the flow fronts to every single part should be the same. The part on the left will have unequal material flow. The one on the right, since it splits off in only 2 sections at a time, this will allow the flow through these different cavities to be the exact same, which is the idea behind having more than one cavity. In the very bottom picture, we have how a runner should be cut into the mold. We want half a hemisphere on the top, half a hemisphere on the bottom. What this will do is this will allow the cooling of the runner to be equal. The runners are usually the thickest portion on this part. As plastic flows, it creates fronts, and once where these 2 fronts meet is called a weld line. In plating applications, a visual appearance is a high priority, and these weld lines can be the difference between an acceptable part that meets standards and one that does not. Along with that, this can have a weak point within the part. On the right, we see the end of fill. Once again, this is the last portion of the part that is filled by the material. There will need to be venting in these locations. This will allow the air to escape. This is done through either the parting line or through ejector plates and pins. The bottom shows how the material will orient itself in the direction of flow. This is just like how a stream is. The water in the center of the stream will move faster than the outside edges due to friction. This can change the different properties of the plastic, like plating adhesion as well as strength. The picture on the left shows us a Z-pin. This is often used in injection molding to hold the material on the left side, on the movable side of the mold. This is so that the mold, once again, will not close up on this part. It is done by having this underneath the sprue of the part, and plastic will flow into the space left by the Z. The other job of an injection system is to eject the part from the movable side of the mold, as can be seen in the picture. This is done by, once again, by moving an ejector plate forward with plates or pins. The cooling cycle is usually done by water or air. Water and air both have their advantages and disadvantages. For water, it is efficient, reusable, has a controllable flow and temperature, but it is prone to leaking, as well as needs constant filtering and it has its corrosive properties. Air is less efficient than water, but it's readily accessible, clean, needs low filtering, and is less corrosive. It can actually be more expensive whenever ammonia and compressed CO2 is used. The capabilities we have here at USI is we have a 55-ton injection molding machine. The height between the tie bars, there are 4 steel bars that run in the center of each injection molding machine. The area between this is we have 12 inches in height, 11 inches in width, and the opening stroke is only 10 inches. So this tells me that this is the largest mold that we are able to have at USI. What I would recommend is the 11 by 11 UF321 from the DME catalog. This is 8 inches in width, 10 inches tall, and about 5.5 inches in width. This should fit comfortably inside USI's injection molding machine. The recommended part design would be a dog bone or a tensile test specimen. We use these in the courses offered here at USI to measure the different strengths of materials as well as the percent of elongation. This is done by clamping this part in a machine and stretch it until it breaks. The graph to the right is actually taken from a materials class I've taken here at USI to show the ultimate tensile strength of the material. When I first developed the product, this was the initial design. I had 2 runners going to each side of the part. This does not follow the recommendation set earlier in the presentation. I need to have a uniform thickness throughout this part. So to combat that, I created this part design. We have a 1/4-inch diameter runners going to each side of the part. Once again, I ran into an issue. The issue here is that there would be a weld line in the center of each part. Along with that, the material flow to this would be different. The molecules would be facing in different directions, which means this could compromise the strength of the product. So once again, I redesigned it to create this design. We would need venting at the end of each part. Along with that, I enlarged the runners to maximize flow to this part. The problem with this is that the area was too large. This was about 12 square inches, so 60 tons of force was needed, which was over the amount we have at USI. So my first recommendation was this design. I narrowed the runners to the compromise for the 1.5 times the part thickness. The part's only an eighth of an inch thick. So with this, we need roughly 52 tons of force to create this product. The sprue in the center of the mold will have a diameter of 0.375, and the runners will also be 1/4 of an inch in diameter. This is over the recommended limit, but that was due to any kind of fillers that we were going to put in the material. This is option number 2. I have redesigned the runners as well as gave it a more robust gate. This will allow the material to flow just as efficiently and use less material. So with this, we have 9.8 inches squared. This tells me that we need roughly 49 tons of force to create this product. And finally, the third and my recommended as the best part design is this option number 3. This is 9.4 inches, and this will equate to about 74 tons of force and save USI money on the runner costs. My recommended cooling would be the water. Water flow will need to go from bottom to top on one side of the mold and from left to right on the other. We want the water flow to flow from bottom to top to ensure that no air is trapped within the lines, which can cause the water to be restricted. If the cooling is restricted, cycle times will increase, which will cause processing issues, as well as drive the amount of production down. My ejection system will consist of 4 ejector pins as well as a Z-pin. Once again, the Z-pin will hold the part into the movable side of the mold, and the ejector pin should be enough to eject the part from that side. I chose not to stick an ejector pin in the center due to the fact of this being the critical area. I did not want this to flash over and compromise the strength of the part. When creating this mold, we will have 3 different options. First is to have Dexterous Mold, a local tooling and die manufacturer, create this mold for $3,400. Option number 2 will have them only create the slide-in unit. This means that USI will need to manufacture the outside base. For that, we will need about $1,400 worth of materials, as well as I'm estimating about $600 worth of man-hours, a screw bushing, as well as a locating ring. So the total cost will equal around $4,700. Option number 3, which I don't recommend due to the fact that it provides the least amount of learning, would be to have USI order sheets of plastic from Grainger on average of 31 cents per part. Option number 1 provides the best cost outcome, but it does not provide the most learning, and education should be the key within this project. So option number 2 is the way to go. For $4,700, we will provide the most learning in this process and the processes that are to come. This is where I received my information from, and I want to give a special thanks to the entire SRG Global team, Craig Elpers at Dexterous Mold, and USI, as well as my family, which without them this would not have been possible. If you have any questions, feel free to ask. Thank you.
On your recommended mold, you didn't show where the vents were. How were you going to vent?
Are you talking about on my recommended part design?
Yeah, here.
We will want to put the vents at the end of each location, and depending on the different types of material, we may need a vent in these locations. so that way the air is not trapped in these spots. If push comes to shove, we can actually put a vent right here and right here, but I think that venting at the end of the locations of the parts is all that's needed.
Can you add them after the mold's made? Can you add
Yes,
them?
it's a often practice in injection molding to change the venting location depending on different issues that they may be having in the process.
So, why not start in the middle and let it fill both sides? All three of your designs all fill from one side or the other or both. Why not the middle?
I ruled that out due to that being a critical section. We need to have that to be a equal thickness all the way through due to the cross-sectional area, which we need in the destruction of the product.